So how do you estimate something you don't know? Or rather, how should you estimate it? Let's begin with a simple example. Say that I wish to estimate the mean, say the mean number of pages in library books. You would then go to the library, have a coffee or two, and then proceed to compute the average number of pages in a large number of books, and then assume that this average would be a good estimate of the mean. This makes excellent sense, and often you can find great coffee at the library. And as long as you compute the average over sufficiently many books, the estimate of the mean should be quite accurate. But then, how many books should you average over if you want a certain confidence in your estimate? Let us consider a stationary stochastic process. For such a process, you assume that each value in a realization has the same mean, even though each of the different stochastic variables you observe in your realization might have a different value, just as the number of pages in the different individual library books. But you assume that the mean of the stochastic variables are the same, and therefore it makes sense to compute the average. So if this is a realization of a stochastic process, I assume that the stochastic variables that I assume at every given time point actually has the same mean, but of course I see fluctuations in the observation I observe. But each one of them will have the mean m. Assuming that the process is ergodic, that is, that it is possible to compute the mean, you estimate the mean as the average of the realizations in this way. And it makes perfect sense since you are assuming that each one of them has the mean m, so therefore if you average them you think that that is the value. This is an unbiased estimate. That means that if I compute the expectation of my estimate of the mean, so the my here is the estimate of the mean, that is that I take an average of the different stochastic variables y, and of course then that means also that my my here is in itself a stochastic variable, and I can compute the mean of my mean estimate. That's what I do here. So if I move the expectation inside, like this, and which I'm allowed to do since it's a linear operation, I see that each of my individual means will be m, and if I average over m of them, I will get m. So that means that the mean of my stochastic process is m, which is the same as the true underlying mean, and therefore the process is unbiased. That means that the expected value coincides with the true mean. Obviously this is a highly desirable property in an estimate, but often this is also too much to ask for, and we need often to settle for an estimator that is asymptotically unbiased. That is, if you are given an infinite number of measurements, your average will coincide with the true mean in the limit. The next thing we want of a good estimator is that it is consistent. This means that given enough data, the estimate will coincide with the true value. That is, that it is asymptotically unbiased and the variance will go to zero as the number of observations go to infinity. If we examine the variance of our estimate, then we can write out this as this double sum, which simplifies to this. We can see that this variance will go to zero as long as the autocorrelation function decays sufficiently rapidly to zero, which means that our mean estimate will be a consistent estimator, which is of course a good thing since this is how we always compute the mean. In the case when y is a Gaussian process, one can show that the true variance of this can be expressed as this infinite sum of the autocovariances. This is typically not all that helpful as we do not know these autocovariances, and we would need to estimate those too. Clearly we will not be able to estimate all the autocovariances either if you have a finite set of observations without imposing additional assumptions, but we will return to this issue later. However, the result is still quite useful, and since we are often interested in a white process, and in this case the autocorrelation function has the following shape. It only takes a non-zero value at lag 0, and then all the other values are 0. This means that the expression for the variance will simplify, since all these terms here except for lag 0 will be 0, leading us to this very concise expression for the expected variance of the mean estimate. Given that we assume that the process is Gaussian, we can say that with 95% probability, it will be within the interval plus minus 1.96 times the standard deviation of the noise process. This means that if I wish to determine if the mean of a process is, say, 3, I can form the mean estimate of the average as the average of the observation. Say that I get 5. Is it then reasonable to believe that the true mean is actually 3? Well, this depends on how wide the confidence interval is. That is, how many samples did I average over? Did I use very few observations? I will get a wide confidence interval. Whereas if I used many observations, I will get a much narrower confidence interval. I can therefore form a statistical test to see if the difference that I'm observing is statistically significant. That is the 5 that I observed as the mean estimate, is that a statistically significantly different number from 3? If it is, that means I can conclude that the mean is not 3. However, if it is within the confidence interval, I cannot say that. I can only say that I cannot disprove that the mean is not 3. The difference is not statistically significantly different from 3. This means that the reliability of my estimate depends on how many observations I have. And I can then, prior to actually making the observations, I can examine how many observations do I think I need to be able to make such a call.